Okay, let's continue our study of work by looking at a few special example problems. And remember, why are we calculating work? Well, just for the heck of it right now, but it's going to lead to a super important idea, the idea of energy. And that idea pervades all the sciences, not just physics. So this is the gateway to, to probably the deepest idea in all of science. And the way we understand about energy is through work. So this is not for nothing. We're going somewhere with this. So let's look at this problem. Supposing an apple is lifted straight up a meter, over 3 meters, and then back down a half a meter, and we want to find the work done in that process. Well, the first question you should ask is the work done by what force? Because remember, forces do work, and we have to be clear about what force we're talking about. So let's say we want to find the work done by the gravity force. We'd get a different answer if it was the work done by the normal or the work done by the friction or whatever. But we're going to try to find the work done by the gravity force here. So recall, work equals the force times the distance traveled times the cosine of the angle in between the force and the distance. The black lines here represent the 3 distance vectors, and we can figure out the work done by taking this in steps. In our first step, we are going to have a force of mg directed straight downward. We have a distance of 1 meter directed straight upward, and we have a cosine of the angle between the down force of gravity, the up distance of the distance traveled, and that's cosine of 180 degrees. Those are 180 degrees apart. That's equal to -1. So that would be, for this first leg, that would be a mass of 0.5 times 9.8 times 1 meter up times a -1 for the cos of 180, and that equals -4.9 joules, our new unit. For the next leg, now we have the same gravity force mg. We have a distance of 3 meters, but now notice the angle between our force and our distance, 90 degrees. Cos of 90 is 0. So in our second leg, we do 0 work. And in our last leg, we have the same mg, still down, 0.5 for m, 9.8 for g. G is just a positive 9.8. It's just telling us the size of the gravity force here. And the distance is 0.5 meters. And now all the direction is going to be handled by the cosine function. The gravity is down, the distance is down, there's a 0 degree angle between those, and cos of 0 is 1. So that's equal to 0.5 times 9.8 times 0.5 times 1. That's equal to 2.45 joules. So our 3 works are -4.9, 0, and positive 2.45. Add them all up to get the total amount of work done by the gravity force. The work done by the gravity force equals, I guess that works out to a -2.45 joules. Okay, let's take a look at another example, not with so many steps. Let's take the case of the sun and the earth. The question will be, how much work does the sun's gravity force do on the earth in 1/4 of a revolution? So we'll go 1/4 of a revolution. We'll go from here to here and try to figure out the work done by the sun on the earth. Well, at any given moment, the sun's gravity force pulling on the earth goes straight toward the sun. So that's the gravity force by the sun. We could calculate it using our old universal gravitation if we were so inclined. But let's continue on. So we know the force, and then at any given moment, the distance traveled will be directed this way, tangent to the circle. So the gravity force is straight toward the center of the circle. The distance traveled is perpendicular to that, so that creates a 90-degree angle between the force and the distance. If we calculate the work done, we've got the force, that's the gravity force. We've got the distance, that's however far we've traveled in that little moment. But at any given moment, the angle is 90 degrees between the force and the distance. So the final surprising answer is the sun does no work on the Earth. In fact, anything that travels in a circle doesn't have any work done on it. If you swing a yo-yo over your head in a circle, or in any direction in a circle, that tension force does no work because at all times the force is perpendicular to the distance. In our final example, we've got a lot going on here. We've got somebody pulling a box, 5-kilogram box with a string. There are 4 forces at play: tension, normal, friction, and gravity. And we're going to try to figure out the work done by each of the 4 forces. So let's begin with the gravity force. So we can always just go straight to our work equation. Our force is mg, our distance is d, and let's take a look at our angle. mg is straight down, d is straight that way. That's a 90-degree angle. We got mgd cos of, most importantly, 90 degrees. Cos of 90, 0 joules. The work done by the normal force. Well, kind of doesn't matter how strong the normal force is. It's not going to be quite as big as mg because tension's also going up a little bit. But whatever the normal force is, we've got the same distance of 3 meters, but cos of 90, 0 joules again. So those 2 forces do no work at all. The tension force is, hold on a sec. The tension force is a tiny bit more complicated because that force does do work. The work done by the tension force should equal the tension force times the distance traveled times the cosine of the angle between the force and the distance. That's a 30-degree angle in this problem. So we have our tension force is 8, our distance is 3, and cos 30. And you could type that into your calculator. Make sure you're in degree mode, and you'll get some number of joules. And then our last one is going to require a little bit of thought. The work done by the friction force will be equal to the friction force, whatever its value is. We'll figure that out in a minute. Times the distance traveled, still 3 meters, times the cosine of, well, friction is backwards, distance is forward, that's a 180-degree angle. So cos 180, that's going to equal -1. So the friction force, recall, is equal to the coefficient of friction mu times the normal force times our same distance times -1, the cos of 180. Our mu is given as 0.1, so we know that. Write it down. Our normal force now we're going to have to do a little work to figure out. Let's see, our mg down is 5 times 9.8. That's 49 down. Our tension force in the upward direction is, let's see, we're going to have to break that t up into its components. This shouldn't be scary at this point in the game. So we've got t in the x and t in the y. T in the y direction equals t sine 30. That's 8 sine 30. That's equal to 4 newtons up. So in the downward direction, we've got mg, which is 49. In the up direction, we've got 4 from the tension force. The rest of the up force must be for the normal. 49 down, 4 up, plus another 45 newtons up will give us a grand total of 49 up, 49 down. Perfect. That means we're not accelerating up or down. No net force in the y direction. So our normal force must be 45 newtons times the distance 3 times the -1 from the cos 180, and all together that comes out to -13.5 joules. So there you have it. Many forces at play. Each force does its own amount of work. What I'd like you guys to do is try those introductory problems. Be prepared to show me your answers tomorrow, and we can discuss some other subtleties around the idea of work. Good luck, everybody. See you tomorrow.